Fine, let's start. Number 1. The McKittrick Tar Seeps. Out in the dry hills of western Kern County, California, a steel pump jack rocks up and down against an orange sky. It has been pulling oil from the ground here since the 1890s, but the McKittrick oil field keeps a second secret beneath its dust. Scattered across the field are natural asphalt seeps, black pools of tar that have oozed to the surface for tens of thousands of years. And those pools are full of the dead. McKittrick is a working oil district that is also, quietly, a second La Brea. The seeps trap animals the same way the famous Los Angeles tar pits do. A thin film of sticky asphalt hides under dust or shallow water. A large plant eater wanders in and gets stuck. Its struggles draw predators and scavengers, and they get stuck too. This is why asphalt traps are so strange. The bones that come out of them are heavily skewed toward meat eaters, because one dying animal can lure many hunters into the same trap. The list of what has been pulled from McKittrick reads like a roll call of the Ice Age. Saber-toothed cats, dire wolves, whose scientific name is Enochian dirus, ground sloths, ancient camels, horses, bison. Serious excavations began in 1928, led by the University of California and the Los Angeles County Museum. Many of the fossils date to the late Pleistocene, roughly 38,000 years old and younger, overlapping the same window as La Brea. What makes asphalt so valuable to science is that it excludes oxygen and bacteria. That means delicate things survive: bird bones, insects, seeds, wood, the fragile pieces that usually rot away. The tar stains the bones so completely that specimens often need chemical cleaning before their surfaces can even be seen. Here is the disturbing part. This is not a protected park. The asphalt was mined commercially for road tar, so for years the fossils came up mixed with the industrial product. The San Joaquin Basin around McKittrick is one of the most productive oil provinces in the country, and the tectonics of the San Andreas system built both the oil traps and the surface seeps. The trap is still active today. Modern animals still get mired in the same tar that holds the saber-tooths. If a working California oil field hides Ice Age cats, imagine what waits inside a lake made entirely of tar. Number 2. The Trinidad Pitch Lake Megafauna. On the Caribbean island of Trinidad, in a village called La Brea, there is a lake that is not made of water. It is made of asphalt. Pitch Lake is the largest natural asphalt deposit on Earth, spreading across about 40 hectares, roughly 100 acres, and holding an estimated 10 million tons of pitch. At its center, it is around 75 meters deep, about 250 feet of slowly churning tar. The lake is fed by a deep fault, where oil migrates upward, loses its lighter fractions, and pools at the surface as asphalt. People have mined it since the late 1800s. Trinidad pitch paved the streets of London, of Washington, of New York. As far back as 1595, Sir Walter Raleigh used it to caulk his ships, and pronounced it most excellent. The surface is not solid. It circulates so slowly you cannot see it move, but move it does. Objects left on the pitch are gradually drawn under, and years later they can resurface, transformed. Trees, leaves, and human artifacts have come back up out of the black, and so have the remains of prehistoric giants. A giant ground sloth and mastodon material have been reported from the pitch, preserved by the same airless entrapment that built the California tar sites. The lake is dangerous. It bubbles with methane and other hydrocarbon gases, and people have died after wandering onto crust that was too thin to hold them. Yet it is also a tourist attraction, with guides walking visitors across the firmer zones, the pitch soft in the tropical heat and harder where the weather has cooled it. there is life inside it too. In 2013, a team led by Rainer Meckenstock published work in the journal Science, describing extremophile microbes living in tiny droplets of water trapped within the asphalt. Astrobiologists now study those droplets as models for possible life in the hydrocarbon lakes on Saturn's moon Titan. Local legend tells a darker story, that the gods opened the earth to swallow a village that had eaten sacred hummingbirds. The chemistry is a strange soup of bitumen, clay, and water, and its viscosity shifts with the temperature so that the same spot can be walkable one afternoon and dangerously soft the next. The lake sits right where the Caribbean and South American plates grind together. The very tectonic collision that also created Trinidad's oil fields in the first place. The lake even regenerates. Pitch removed by mining is slowly replaced from below. So after more than a century, it has still not been exhausted. Think about what that means. It is a quarry, a tourist walk, and a graveyard, all at once, still swallowing anything left on its surface. Tar preserves the recent dead. But what happens when the drilling reaches all the way back to the age of dinosaurs? Number 3. The Alaska North Slope polar dinosaurs. Far above the Arctic Circle, along the Colville River on Alaska's North Slope, the frozen ground holds something that rewrote the rules for dinosaurs. The rocks here are called the Prince Creek Formation, and they date to the late Cretaceous, roughly 69 to 73 million years ago. Back then, this land already sat at a paleo latitude of about 80 to 85 degrees north, deep inside the Arctic. These dinosaurs lived through months of winter darkness and near freezing cold, shattering the old assumption that all dinosaurs were tropical animals. The signature species is Pachyrhinosaurus paritorum, a horned dinosaur with a thick, bony boss where a nose horn would be. It was named in 2011 by Anthony Fiorillo and Ronald Tukoski, and its name honors the Perot family for their museum support. Alongside it lived a duck-billed hadrosaur named Ugrunaluk in 2015, drawn from the Inupiaq language, though scientists still argue whether it is its own species or a young Edmontosaurus. And hunting them was Nanuqsaurus, the polar bear lizard, a small Arctic tyrannosaur described in 2014. Now here is the connection to oil. The reason geologists were up there at all was petroleum. The bones were first collected in 1961 by a Shell oil geologist named Robert Liscombe, who thought they were mammal fossils and set them aside. They sat unstudied in Shell's collections for 2 decades before anyone realized they were dinosaurian. The main quarry is now called the Liscombe Bone Bed, and just 7 years after Liscombe's discovery, in 1968, the giant Prudhoe Bay oil field was found nearby, the largest oil field in North America. The infrastructure and geological mapping that came with that oil rush is what put scientists within reach of these bones. The bone beds are packed with juveniles, which suggests something remarkable. These hadrosaurs may not have migrated thousands of miles. They may have nested, hatched, and raised their young right there in the polar dark. Tiny hatchling teeth and bones support the idea of year-round residency. Small feathered dinosaurs in the same rocks hint that insulation helped them survive the cold. The exposures are brutally remote, reachable mainly by bush plane and boat, and they erode every summer, dropping fresh bone straight into the river. Anthony Fiorillo of the Perot Museum has led expeditions here for decades. The Arctic oil that gave America Prudhoe Bay crude also handed us proof of dinosaurs breathing in the frozen dark. And if Arctic oil exposed dinosaurs, what do the largest oil mines on the planet dig up? Number 4. The Athabasca oil sands sea monsters. In northern Alberta lie the Athabasca oil sands, one of the largest hydrocarbon deposits on Earth, holding somewhere between 1.7 and 2.5 trillion barrels of bitumen in the ground. The tar sits inside the Cretaceous McMurray Formation, sands laid down about 110 to 115 million years ago. To reach it, mining companies strip away the overburden with enormous shovels. And every so often, those shovels bite into a buried ocean. The most famous discovery came in 2011 at the Suncor Millennium Mine. A shovel operator uncovered Boreolopelta markmicheli, an armored nodosaur so well preserved it looks less like a fossil and more like a sleeping animal turned to stone. It still has its skin, its armored plates, and even chemical traces of its reddish coloring, work led by Caleb Brown of the Royal Tyrrell Museum. This was a land animal, yet it was found in ocean sediments. It likely died on land, washed out to sea, and sank belly up into the marine mud. A study in 2020 found ferns and charcoal in its stomach, evidence it had been grazing on a recently burned landscape. It was so heavy and fragile that machinery accidentally broke it, and a technician named Mark Mitchell spent more than 7,000 hours preparing it, which is why the species carries his name. But Boreolopelta is only the beginning. These sands and the seas above them have yielded ichthyosaurs and plesiosaurs, the long-necked reptiles of the western interior seaway that once split North America in two. That same sea gave us ammonite, a gem of shattered rainbow, color made from the fossilized shell of the ammonite placenticaris. Ammonite was granted official gemstone status in 1981, one of the only gems made from a living thing. Giant predators swam here too, mosasaurs, and the fanged fish Cephactinus. Ammonite is a story of its own. It forms only where an ammonite shell was buried fast and squeezed under just the right pressure to keep the original mother-of-pearl layer, called nacre, intact, and it flashes green and red and gold like a shattered opal. Most shells never make it. The odds against any given ammonite becoming gem-grade ammonite are staggering, which is what makes the Alberta deposit so prized. Under Alberta's heritage law, companies like Suncor and Syncrude work with paleontologists to recover what the mining exposes. Many of these specimens end up at the Royal Tyrrell Museum in Drumheller, one of the great dinosaur collections on Earth. And the truth is that this industrial earth-moving unearths more fossils than any careful academic dig ever could. The very oil in the sand is derived from the marine life that the mining reveals. Draglines and 400-ton trucks carve into black tar and lift out sea dragons and rainbow shells. These fossils sat above the tar. But what about oil drilled straight through an actual fossil reef? Number 5. The Permian Basin Reef Cores. The Permian Basin of West Texas and southeastern New Mexico is the most productive oil region in the United States, pumping millions of barrels every single day. And nearly all of that oil is bound up with an ancient reef. Around the rim of a deep marine gulf called the Delaware Basin, a great reef grew between roughly 260 and 265 million years ago. It was not built by corals. It was built by sponges, algae, bryozoans, and microbial communities in a warm, shallow, tropical Permian Sea. When that sea eventually dried and was buried under thousands of feet of sediment, the reef went with it. Today, oil wells across the basin drill straight through it, coring up crinoids, brachiopods, ammonoids, and tiny rice grain foraminifera called fusulinids. Those fusulinids are so abundant and so tied to specific slices of time that geologists use them to date the oil-bearing rock. The reef's porosity, all that space left behind by ancient organisms, is exactly what makes it hold oil now. The creatures that built the reef also built the reservoir. You do not even have to drill to see it. The same reef system is spectacularly exposed at the surface in the Guadalupe Mountains and at Carlsbad Caverns, which let geologists study what they are drilling through underground. The geologist Philip B. King mapped that reef in the mid-20th century, and his work became the foundation for understanding the buried oil geology. Production here began in the 1920s and has never really stopped, right up through the modern Wolfcamp shale boom. There is a darker chapter written into these rocks. The Permian ended in the largest mass extinction in Earth's history, about 252 million years ago, when an estimated 90% of marine species died. Many of them were the very reef builders now pumped for crude, and the caves themselves are part of the same story. Carlsbad caverns were carved when sulfuric acid, tied to the oil and gas below, dissolved the reef limestone into vast underground halls. The oil in the caves are both children of the same buried reef. So every barrel from the Permian Basin is drawn up through the skeleton of a 260 million year old reef teeming with extinct life. On land, the drills hit a reef, but offshore, in the Gulf, they hit the ghost of a whole dried up sea. Number 6. The Gulf of Mexico Salt Dome Cores. When oil companies drill in the deep water of the Gulf of Mexico, they run into a wall that most people never hear about. Before they can reach the oil, they have to punch through thousands of feet of ancient salt. This is the Luan Salt, laid down about 170 million years ago in the Jurassic, when the young Gulf was a restricted basin that flooded and dried again and again. Each time the seawater evaporated, it left salt behind until the beds grew thousands of feet thick. It is the crushed chemical corpse of an entire evaporated sea. Salt is strange. It is less dense than the rock piled on top of it, so over millions of years it flows upward, rising into domes, sheets, and pillars miles tall. Geologists call this halokinesis. Those rising salt structures create the traps that hold much of the Gulf's oil and gas, which means the industry is quite literally drilling into a dead ocean's mineral skeleton to reach the crude. In 2010, the Deepwater Horizon disaster happened at the Macondo Prospect, a deepwater play beneath the salt, a grim reminder of how deep and dangerous this drilling is. Below and around the salt, the sediments are full of microfossils, foraminifera, and nanoplankton, and biostratigraphers use them to date each layer and steer the wells. Because pure salt holds almost no fossils, drillers actually know they have entered the ancient evaporate sea by the sudden silence in the samples the moment the microfossils disappear from the cuttings. The leading edge of these flowing salt sheets forms a feature on the seafloor called the Sigsbee Escarpment. This is a different beast from the Mediterranean's famous salt crisis. That Messinian salt is far younger and formed when an existing sea dried out. The Gulf's Luan is older and formed as the supercontinent Pangaea tore apart. Salt makes such a perfect seal for oil because it is impermeable, and it flows to close its own cracks, which is why so much Gulf oil hides beneath it. The caprock that forms on top of many of these salt domes holds its own surprises. It often contains native sulfur, mined for decades, and sometimes seeps of petroleum, so the domes are treasure and hazard at once. And because the salt keeps flowing, it can deform and even pierce the very oil reservoirs it helped create, a sea that refuses to stay buried, still shouldering its way upward after 170 million years. And there is a final twist. Caverns leached out of these same salt domes now hold the United States Strategic Petroleum Reserve, a Jurassic sea, dead for 170 million years, literally stores the nation's emergency oil. Platforms floating in a mile of water drill miles down into that dead sea. But some oil rock is not chemistry at all. Some of it is a field of preserved life. Number 7. The Green River Oil Shale Fossils. Spread across Wyoming, Colorado, and Utah is the Green River Formation, the largest oil shale deposit on Earth, holding an estimated 1.5 trillion barrels of oil equivalent, and by some counts far more. But this oil is not liquid. It is kerogen, solid organic matter locked in the rock, which has to be heated before it will give up oil at all. That is why it is called oil shale. And the same thing that concentrated all that organic matter also created one of the most beautiful fossil sites in the world. The formation is the bottom of a set of enormous lakes, Fossil Lake, Lake Gosute, and Lake Uinta, that existed about 53 to 48 million years ago in the Eocene. The lake floors held stratified, oxygen-poor water where nothing could scavenge or decay. Anything that sank was preserved in exquisite detail. In the quarries near Kemmerer, Wyoming, and at Fossil Butte National Monument, the fish come out perfect, whole skeletons with scales and fins intact. Nitia, the Wyoming state fossil, Diplomistis, Priscacara. There is even a famous slab showing a bigger fish frozen in the act of swallowing a smaller one, caught at the exact moment of death. And it is not just fish. The Green River has produced fossil birds, some of the earliest known bats, Icaronectaris and Onychonectaris, crocodiles, turtles, snakes, insects, leaves, and even flowers. The rock is layered in fine light and dark bands called varves, one pair for each year, so scientists can literally count time like tree rings. The richest, brownest layer of oil shale is nicknamed the Mahogany Zone. Paleontologist Lance Grande of the Field Museum has spent decades documenting this lost Eocene world of warm lakes and lush subtropical forests. Commercial interest in the oil has boomed and collapsed over and over since the early 1900s, because extracting it takes enormous heat and water. That difficulty has, almost by accident, helped protect the fossils. Think about the strange overlap here. The biggest untapped oil deposit on the continent is also a mass grave of Eocene fish, birds, and mammals, preserved in the middle of life. You cannot separate the fuel from the fossils. They are the same compressed lake sludge. Shale freezes the dead in stone, but there is another kind of oil country that freezes them whole. Number 8. The Siberian oil and gas field mammoths. In the far north of Siberia lies the Yamal Peninsula, the heart of Russia's largest natural gas province, home to the giant Bovanenkovo field. In the language of the Nenets, people who herd reindeer across it, Yamal means the end of the earth. And the frozen ground here is a natural freezer that has kept the ice age intact for tens of thousands of years. As gas development and a warming climate disturb that permafrost, it keeps giving up the dead. In 2007, on the Yamal Peninsula, a Nenets herder named Yuri Kuti found the most complete baby woolly mammoth ever discovered. She was named Lyuba, and she is about 42,000 years old. Her skin, her trunk, even her last meal preserved. Elsewhere in the Siberian permafrost, a mammoth called Yuka came out with reddish fur and soft tissue still attached. The cold halts decay so completely that woolly rhinoceroses, cave lions, bison, horses, and wolves have all emerged with fur, skin, and organs intact. But the moment air reaches them, the clock restarts, and they begin to rot within days. Then, in 2014, something genuinely frightening started happening. Giant craters began appearing on the Yamal tundra, some tens of meters across, at first with no explanation at all. Researchers eventually linked them to explosive releases of methane gas, built up under pressure in thawing mounds of ice called pingos, and blown open like a cork out of a bottle. That methane is tied to the same gas-rich geology that makes Yamal such a hydrocarbon treasure house. The peninsula supplies a huge share of Russia's and Europe's natural gas. Scientists at the Northeastern Federal University in Yakutsk study these carcasses, and some of the preserved blood and cells have fueled proposals to bring the mammoth back through cloning, though no living cell has ever been recovered. Meanwhile, mammoth tusks feed a large ivory trade, sometimes uncovered near resource operations. And the released methane is itself a powerful greenhouse gas, feeding back into the warming that thaws the ground. Picture it. Gas rigs and pipelines stretched across a tundra that periodically explodes and coughs up 40,000-year-old mammoths. Buried giants, explosive gas, and a thawing climate, all stacked over one of the richest energy zones on the planet. These are giants you can see. But the drillers date every single well, using things far too small for the eye. Number 9. The microfossils that built petroleum geology. Here is a secret about the entire oil industry. It runs on fossils too small to see. Every well drilled anywhere on Earth is dated using microscopic remains that come up mixed with the mud, a science called biostratigraphy. The stars of that science are the foraminifera, single-celled marine creatures that build intricate shells, along with nanoplankton, diatoms, ostracods, and fossil pollen. Foraminifera first appear in the fossil record back in the Cambrian, and across that vast stretch of time, they evolved into countless distinct species, each one living only during a narrow window. That is the key. If a micropaleontologist finds a particular species in the cuttings, it tells them exactly how old that rock layer is. This is how drillers know where they are, thousands of feet underground in the dark. The discipline exploded in the early 1900s precisely to serve the oil hunt, and some of its most important pioneers were women. Around 1920, Esther Aplin, Alva Ellisor, and Hedwig Neiker proved that foraminifera could reliably correlate oil wells across the Gulf Coast. The idea was met with open skepticism at first. Then it revolutionized exploration and became standard practice at every major oil company. So many geologists were hired to pick these tiny shells out of samples that they earned a nickname, the bug pickers. The forams themselves range from smaller than a grain of sand to a few centimeters across, washed and sieved out of the cuttings. The floating planktonic kinds are best for dating. The bottom-dwelling kinds reveal how deep the ancient water was. Larger foraminifera, called fusulinids, are prime index fossils for the Pennsylvanian and Permian oil rocks, including that Permian Basin reef. Even smaller are the nanofossils, calcareous plates from algae, which need an electron microscope to see. The White Cliffs of Dover are made of those same nanofossils that help date offshore wells. Where marine microfossils run short, palynologists read fossil pollen instead, and the oil itself is generated from the plankton associated with these very microfossils, buried and cooked over millions of years. So humanity finds most of its oil and dates most of its oil, using the shells of creatures no eye can see. Entire invisible ecosystems steer the drill, and one single well, drilled in 1859 over a Devonian sea, started all of it. Number 10. The Drake Well and the Ancient Devonian Sea. Near the town of Titusville in northwestern Pennsylvania stands a replica of the well that started the modern world. The Drake Well is widely regarded as the first commercially successful oil well ever drilled specifically for oil. It was completed on August 27, 1859, by a former railroad conductor named Edwin Drake, working for the Seneca Oil Company. He struck oil at a depth of only about 69.5 feet. His great innovation, worked out with a driller named William Uncle Billy Smith, was a driven iron pipe that kept the loose ground from collapsing into the hole. That single well set off the Pennsylvania oil boom. Within a few years, thousands of derricks crowded the banks of Oil Creek, and the price of oil swung wildly between fortune and glut. Kerosene refined from this oil replaced whale oil in lamps, reshaping the world's economy and taking pressure off the hunted whale populations. But the strangest thing about the Drake Well is not the machine. It is what the oil actually was. The oil Drake tapped was manufactured by a sea. During the Devonian period, roughly 380 to 360 million years ago, much of what is now Pennsylvania lay beneath a warm, shallow ocean on the margin of an ancient continent. That sea swarmed with life. Trilobites, brachiopods, crinoids, corals, and armored fish called placoderms, including the giant predator Dunkleosteus. The Devonian is even nicknamed the Age of Fishes, home to the first sharks and to the lobe-finned ancestors of every land animal, including us. When the plankton and algae of that sea died and sank into oxygen-poor mud, they were buried and slowly cooked into crude oil. The Marcellus Shale, a black Devonian rock that is now a major fracking target across the same region, is the very source rock, and its richness comes from the dead plankton of a stagnant Devonian seafloor. Near the end of the Devonian came one of the great mass extinctions, wiping out much of that reef and marine life, the same life that became the source rock. So the first oil well in history pierced ground, built by a 380-million-year-old sea, and drew up the transformed bodies of its long-dead creatures. Every well since is descended from Drake's, and Drake himself died poor in 1880, never having patented his method, even as the industry he founded made others unimaginably rich. Step back from the 10 sites, and a single idea ties them together. Petroleum is fossilized life. Oil is what happens to the buried bodies of ancient plankton and algae after millions of years of heat and pressure, which means that oil ground is always fossil ground, and drilling for oil is always, in some sense, digging into deep time. Look at the preservation modes we have seen. There is tar and asphalt at McKittrick and Trinidad, which swallows whole recent megafauna and holds them airless for tens of thousands of years. There is marine sediment and stone in Arctic Alaska, in the Alberta oil sands, in the Permian Reef beneath the Gulf Salt, which preserves whole ancient seas and the reefs that ring them. And there is Lake Shale and permafrost in the Green River and on Yamal, which keeps the most delicate bodies of all, fish caught mid-motion, mammoths with their last meals intact. The reason these keep overlapping is not coincidence. Oil forms where dead organisms pile up in water, starved of oxygen, because oxygen would otherwise rot them and burn away the carbon. That exact same lack of oxygen is what preserves exceptional fossils. The conditions that make a great oil source rock are the conditions that make a great graveyard. On top of that, the rock that stores the oil is often built directly from organisms, from reefs and shell beds, and the seals that trap the oil, salt, and shale trap the fossil record too. So exploration geology and paleontology are really the same search carried out at different scales, and micropaleontology is the bridge between them. It is worth sitting with the strange truth that the largest fossil exposures on the planet are not academic digs at all. They are mines and rigs, moving more earth in a day than a museum crew moves in a decade. Drilling for oil is a kind of accidental time travel, straight down through stacked layers of dead worlds. And there is a final irony folded into it. When we burn that oil, we release the carbon of ancient life back into the modern sky. It is worth looking closer at why oil and fossils are chemically bound together. Oil forms in what geologists call the oil window, when a source rock is buried deep enough to be heated to roughly 60 to 120 degrees Celsius over millions of years. In that range, the solid organic matter, called kerogen, slowly matures into liquid oil and gas. Too shallow and cool, and it stays raw kerogen, as in the Green River Shale. Too deep and hot, and the oil itself is destroyed. That temperature story is also a preservation story. The delicate fossils survive best in cool, shallow traps, tar seeps, lake beds, permafrost, where heat never reached them. The richest oil, by contrast, comes from deeper, hotter rock, where any bones would have been cooked away. In between lies a sweet spot where preservation and hydrocarbons can coexist, which is why offshore cores tend to give up microfossils rather than skeletons. The seals matter too. Salt and shale trap hydrocarbons because they are impermeable, and in doing so, they also seal off and protect the layers beneath. Reef and shell rock hold oil because the ancient organisms left behind pore space. Everywhere you look, biology built the plumbing. The record of time is written right into these rocks. In the Green River Shale, those paired light and dark laminae are varves, one couplet per year, so a slab of oil shale is also a calendar that can be counted layer by layer. In the deep marine sediments, it is the microfossils that keep time, each species marking its own narrow interval. The rock does not just hold the oil, it holds a clock. And here is the most remarkable part. Even when there are no bones at all, the oil carries a fossil signature. Crude contains biomarkers, molecular fossils, specific compounds that survive from the original organisms. Geochemists can pull a vial of oil and read the chemistry of the plankton that made it, identifying the kind of algae, the ancient environment, even the age. Oil is a chemical mummy of a vanished ecosystem. Each of the 10 sites is just a different point on one continuous spectrum, running from a whole frozen mammoth at one end to a molecule of dead algae in a barrel of crude at the other. For all of this, the drill reaches places science rarely samples on purpose, and that leaves real mysteries behind. Take the Arctic dinosaurs. We still argue about whether those hadrosaurs migrated south each winter or toughed out the polar dark year-round, and we are not even certain that Ugranaluk is a valid species rather than a juvenile of a known one. The evidence is buried in ground that is almost impossible to excavate. The tar and ice hold their own unknowns. Nobody knows how many Megafauna Trinidad's pitch lake truly contains, because you cannot dig a lake that swallows its own record. Nobody knows how many mammoths still lie locked in the Yamal permafrost, or whether a viable cell could ever be recovered to attempt de-extinction. The number and exact cause of the Siberian methane craters are still debated, even as new ones appear. Then there is everything lost without a witness. How many fossils are destroyed unnoticed in the daily churn of oil sands mining, or crushed in the Permian cuttings and never studied? How much of that ancient reef biota vanished up a drill pipe? Some asphalt fossils resist precise dating because the tar contaminates the chemistry. Biomarker science can identify broad groups of source plankton, but often not the exact extinct species. And deeper, hotter basins may once have held rich fossil records that the very heat which made the oil has since erased. Even the well-studied sites keep their secrets. Geologists still debate the exact depth and chemistry of the Green River lakes, and how warm the North Slope really was when dinosaurs nested there. And we will never know how many Devonian fossils were smashed and discarded in the frenzy of the first Pennsylvania oil boom, when nobody was looking for anything but crude. This is the honest tension at the heart of the subject. Absence of evidence is not evidence of absence. Industrial access to the deep earth is vast, but uneven, and most of what comes up is never examined by a scientist at all. The drill is the best window we have into these buried worlds, and also one of the most careless. So, where is this collision of oil and deep time heading now? Increasingly, industry and science are formally linked. Heritage laws in places like Alberta require fossils exposed by mining to be recovered, and paleontologists are embedded with operations to salvage them. Seismic surveys and core data originally shot to find oil are being reused for pure science, including the mapping of drowned prehistoric landscapes on the seafloor. Some of the most striking work reaches toward the future. De-extinction teams are targeting the woolly mammoth using genetic material from permafrost specimens like those emerging on Yamal. That same warming climate is accelerating the exposure of frozen megafauna, even as it makes the methane craters a hazard that scientists now monitor closely. The great salt caverns of the Gulf, leached from that dead Jurassic Sea, still hold the nation's strategic petroleum reserve. And micropaleontology, the science of the bug pickers, now guides not only oil wells, but carbon storage projects, as depleted reservoirs and deep saline aquifers are repurposed to bury carbon dioxide back underground. Museums have grown from this, too. The Royal Tyrrell in Alberta and the Perot in Texas were built in part on fossils that industry uncovered, and their galleries now teach millions of visitors a science that began at the bottom of a drill hole. Astrobiologists keep returning to Trinidad's Pitch Lake and its tar-dwelling microbes as a model for life on Titan, reasoning that if microbes can live in asphalt on Earth, they might survive in the hydrocarbon seas of a distant moon. Arctic expeditions still work the Colville River each summer, and in a quiet twist, the collapse of commercial interest in Green River oil shale has helped preserve its fossil beds. The pattern holds for now that new drilling means new fossils. But the energy transition is beginning to change what we drill and where and how much, which means this strange golden age of industrial paleontology may not last forever. In the end, oil is the transformed substance of ancient life, and to drill for it is to reach a hand into a graveyard of deep time. That is the thread running through all 10 of these disturbing finds. Remember the saber-toothed surfacing in a California pumpjack field, the ground sloth sinking into a Trinidad pitch that people still walk across, dinosaurs breathing in the Arctic dark near Prudhoe Bay, sea dragons and rainbow shells lifted out of Alberta's black sand. Remember the Permian Reef pumped through Texas wells, the Jurassic Sea crushed to salt beneath the Gulf, the Eocene fish frozen midlife in the world's largest oil shale, the mammoths rising out of an exploding Siberian gas field, the invisible shells that steer every drill on Earth, and the first well of all, sunk over a Devonian sea, more than 300 million years dead. Put them together, and one quiet realization emerges. Energy and extinction are written into the very same rock. We power modern life by burning the buried remains of older life, drawn up from cemeteries of vanished oceans. The drill is a needle threaded into the deep memory of the planet, and almost every time it goes down, it touches something that was once alive. Maybe that is the real gift hidden in all these grim discoveries. They remind us how much world came before us, layered beneath our feet, patient and enormous and mostly forgotten. The next time you pass an oil field or a gas flare on the horizon, you might see it a little differently. Not just as machinery pulling fuel from the ground, but as a slow excavation of the dead, and a strange, accidental conversation with everything the Earth has ever been.